Okay, so here we go with Classwork 10 regression models. In this classwork, we're going to work on connecting the models we've been talking about with the more formal regression models. So let's start with interpreting models. Let's say that you're a social justice oriented restaurateur and you're thinking about opening a few trendy pizza shops in LA. You're thinking about setting a few different price points for your pizzas. In an upscale area, you want to charge more, and in a working class neighborhood, set the prices a little lower. You want to know how to price your pizzas and toppings, so you decide to look through a set of data collected on 12-inch pizzas sold in the area. Each pizza was coded for 1. Where it was sold in the city, 2. How many toppings are on it, and 3. The price of the pizza. Let's start by opening up the data file in Canvas. To do this, we're going to go to our Canvas homepage. Then click on Modules, and you'll find it under this week's module. It's called pizzaprices.jasp. Click on the data link and then click Download pizzaprices.jasp. If you have JASP installed on your computer, it should download right away, although it may look a little different from my version. On mine, I can simply click it and it will open up JASP for me. So here we have the data set. So we can see in the data file that the pizzas are coded for the part of the city, the number of toppings, and the price of the pizza. In the data set, each row or each case represents one 12-inch pizza. So let's look at pizza number 15. This pizza was ordered in a hipster part of town, had 4 toppings on it, and cost $17.48. So each of these cases tells us about one pizza in the data set. Since you're interested in figuring out pricing, let's start by making a super simple model like the ones we did in classes 7 and 8 that will help us get an initial idea of what the price of pizzas look like in this area. So our simple model is based off of this modelese, as I like to call it, or this model language that we've been using so far. So the modelese says data equals mean plus residual, or as I prefer, the term error. So this is not a great model, but it is a really simple one. Thinking back to the models we drew before, if you remember the hint, think shape center spread, and then writing out the model, if you think you know what I'm talking about, then I would say go ahead and pause the video here and draw out the model and write out the model for this. Then come back and join us. And if you're not sure what that would look like, then just go ahead and keep watching. First, let's see where this information in the workbook came from, as this is coming from our data set in JASP. So to get this information, we would go to descriptives, descriptive statistics, and then we want to look at which variable, price of pizza. So I'm going to select price of pizza and put it in my variables box. As you can see, this is how we got this table of information. Now, to get the plot or graph, we have to click on the little arrow next to plots to expand the menu, then select for distribution plots. Then I'm going to click OK so that we can see this a little better here. And we can see that this is where our graph and table came from. So let's go back to creating our simple model. So keep in mind that the data we see is data from a sample. It's not data for every 12-inch pizza that was ever sold in Los Angeles. When we build our model, we always want to build it to represent the bigger population. When we draw the shape on our model, we're drawing what we think the shape of the population this sample of data came from might look like. What does that population maybe look like? So I can see that it looks roughly normal to me. So I'm going to sketch out a roughly normal shape representing the population that I think this data may come from. I'm going to do my best to center it around about 14, so probably around about here. Any, and again, this does not need to be perfect by any means, just a rough idea of the shape. Theoretically, I think that this is probably about the shape of the population that this sample came from. Next, I want to indicate the center. So as I mentioned previously, on these simple models, we represent the center using the mean. In this case, I'm going to set my mean just a little bit past 14, and I'm going to label it so that it's clear that it's supposed to represent the mean of the population. The symbol that I'm going to use for that is the Greek letter mu, since that represents the mean of the population. Okay, so we've got shape and center. Next up is spread. On our simple model, we represent the spread using the standard deviation, which is 4.184. That's roughly what we would expect for the standard deviation in the overall population. So if this mean here is a little bit above 14 and the standard deviation is a little bit above 4, then if we take the difference, we're looking at about 10. So what we're saying is that we see the average spread of about 4 either side of the mean. You could draw it on the left, you could draw it on the right, you could draw it up higher, you could draw it down lower. But as long as you're representing that average spread around the mean by indicating this population standard deviation, sigma, that's what I'm looking for. So let's connect this with the modelese. So data equals mean plus error. The dependent variable here is what we're trying to predict or explain. So let's connect this with the modelese. So we have data equals mean plus error. The dependent variable here, or the dv, is what we're trying to predict or explain. In this case, that would be the pizza price. So price of pizza equals to the center, which in our simple model is going to be the mean. So let's plug the mean in here. And then you can always leave this plus error or plus or minus error to account for the fact that it's lower or higher. You could also plug in the standard deviation here, so 4.18, or writing SD. Any of these I would give credit for. I just want to make sure that they're represented in the model. Okay, so remember that statistics is about being less wrong. If we had more information, like the number of toppings, which we do, we might do a bit better in explaining the variation that we see in pizza prices in the LA area. Let's begin the process of improving our simple model a bit by adding on toppings, and we'll call this the topping model. First, let me walk you through how to get this graph from the data in JASP. So we're going to come up to JASP, and then we want to select the regression button from the buttons at the top, and then select correlation matrix. Now our correlation matrix shows up blank because we haven't told JASP which variables to compare yet. We want to look at the price of pizza versus the number of toppings on the pizza. Now I still don't have that graph, So to get that, I'm going to go under Plots and select Correlation Matrix. Now it's going to maybe look a little different from the workbook because it's a different version of JASP, but this is where this graph comes from. So we can see the relationship between the number of toppings on the pizza. So down on the bottom, you can see the 0, 2, 4, 6, 8. That's how many toppings there are. And then on our y-axis, we can see how much the pizza cost. So for the shape, we make the scatter plot. And remember that the x-axis is on the bottom and the y-axis is the one over on the side. Okay, now center. When we're working with a model with two variables, we can't just give the mean of one variable as the center. What we do is we find the center in terms of balancing all the data points. As you can see, JASP automatically draws in the center for us by drawing in the regression line for us. This line that we see was calculated from our data by JASP so that it balances all of the differences above and below the line. These differences between what we would predict based on the line and an actual data point, for example, this one here, that difference is called the residual. It's the residual, the leftover, or the error between this actual data point and what we would predict for a pizza with, say, 4 toppings. The regression line is calculated so that it balances all of the residuals from the data set that are above the line with all of the residuals that are below the line. So once again, the center is the balancing point. Now this brings us to spread. So on this part, I want you to draw in a few of those residuals to illustrate the spread. They should always go straight up and down, and here's why. Okay, so if I have a pizza with 0 toppings, then I would predict the price based on where the line is hitting at x equals 0. If I was predicting for a pizza with 2 toppings, I would look where the line is for x equals 2 and use that to estimate the price of the pizza. We can see when x equals 4, where there's 4 toppings, that based on the line, I would estimate the price maybe around $12 or $13. And we can see here that there are a lot of pizzas that cost more than that had 4 toppings on them, but we also see in other places that there are pizzas that cost less than what we would predict. Those differences between the actual data point and what we would predict for the value of that value of x, that's our residual. And that's showing us how much spread there is away from that center line or that regression line. Now, JASP will calculate everything that we need for our regression model, so we don't have to calculate anything by hand. To see the written instructions on how to do this, I recommend flipping back to Appendix A in your workbook and finding the section on running a regression. The first thing we need to figure out is what is the dependent variable and what is the independent variable. Remember, the dependent variable is the one that we want to explain or predict. So in this case, we're trying to explain or predict the variability that we see in pizza prices. So what is the covariate, or aka the independent variable? Covariate is just another way of saying independent variable. Well, in this model, what do we think is influencing the price of the pizza? So in this case, our independent variable or covariate is going to be the toppings. Okay, now let's take a moment to connect the formal notation from the video lectures on regression to the modelese, or that language of models that we've been using in class that comes from the reading we had earlier this semester from David Kenny's book. So here we could see the formal notation for a regression line. Let's revisit the modelese from the reading that we had. You may remember it looks something along the lines of dependent variable, or dv, is equal to some constant plus the effect of the IV, or independent variable, and then we always put some extra error that we can never fully account for or get rid of at the end of our model. So now let's connect these two things together, the regression equation and our modelese. So in this case, the y in the equation is just referring to the dependent variable. So what is your dependent variable? Make sure you always put that on the y-axis. Again, the y-axis is the up and down axis. We always put our dependent variable over here, and we put our independent variable on the x or horizontal axis. So that's going to give us a hint for another piece of our puzzle over here. But first we have the constant. This b sub 0, which is pronounced b naught, that is our constant. What this really is, the interpretation of this is really the y-intercept. What I mean by the y-intercept is this is the value where our regression line crosses the y-axis, where x equals 0. So it's important to remember that this constant represents the y-intercept, or the value that we would get for y if x was equal to 0. Now the next part, the plus b sub 1x, now the effect of part of our modelese is really the b sub 1 part of our regression equation. The IV itself, just like the dv is y, the IV is the x. Whatever we have for our independent variable, we plug it in for x, and then it will have this much effect, b sub 1, on our y. This b sub 1 is the slope of the line, meaning that as our x value goes up by 1, then our y changes by that much, the b sub 1 number. I say y changes because it could go up or down by whatever number is in our equation for b sub 1, depending on if our output gives us a negative or a positive number for b sub 1. That tells us if the y is going to change up if it's positive and it's plus, or if the y is going to decrease and change in the negative direction and go down. So you see the equation y equals b naught plus b sub 1x, the regression equation, is really just another version of the model that we've already been using. You just need to learn which pieces correspond with which pieces from the model and the equation. The dv is the y, and that goes on the y-axis. The b naught is the constant, and what that is when x equals 0, that tells us where our regression line will cross the y-axis. The effect of IV, that b sub 1x, that tells us if x changes, if I add a topping, if I go up by 1, then how does the price of the pizza change? The slope lets us see the effect of the independent variable on the dependent variable. So we can see what is the effect of adding one more topping, or one more topping, or one more topping. That effect of adding one more x, that is the slope. That's b sub 1. So each time x goes up, then the y would change up or down based on what that value, b sub 1, is. If it's down, then we would actually have a minus in between the b sub 0 and the b sub 1. Okay, so now we've connected the pieces, but what we want to actually write out is the formal regression equation, because this is what you would report when you report out your findings. So just so we have some more space, I'm going to rewrite this regression equation right up here. Now we want to fill in the numbers that go in for our constant and the increment for each topping. So our b sub 0 and our b sub 1. Now this information is going to come from our output from JASP. So we're going to switch back over so I can demonstrate how we do this in JASP. Again, we're going to go into regression, and this time we're going to run a linear regression. The second option that you see is the one you want to select. Now this is where it matters which one of our variables is our dependent variable and which one is our independent variable. So if you remember, previously we wrote that our dependent variable is the price of pizza, and our independent variable, or what we're going to end up putting into our covariate box when we switch back, is the toppings. So we have price of pizza was our dependent variable. It's what we're trying to explain or predict. And toppings is our covariate or independent variable. We want to see what effect does the number of toppings have on the price of the pizza. Now, once you've entered that information, you can ignore all of the other menus and click OK. Now you'll be able to see where this information came from. It came from this output. So in the output, we see linear regression. We get a model summary first, which we'll talk about in a moment. Then we get what's called an ANOVA table. We won't really be talking about this until much later on in this class. And then we have the coefficients table, which is what allows us to build our regression equation, which is what we want to do now. So from here, we're going to plug in the numbers for our constant and our slope, and those numbers are going to come from this output here, the coefficients output. So our equation will be y equals the constant. So here we need to figure out what number goes in for the constant. Here we want to look at the very first column in our output table, the unstandardized column. Now remember above I said that the constant is also the y-intercept? Well, here it's labeled in the row when we go back to our output table that says intercept. So we want the unstandardized number for that first row, so we would plug into our equation for the constant 9.51. I'm just going to round to 2 decimal places. It's okay with me if you in this class also round to 2 decimal places. Okay, so 9.51, and that takes care of the first part of the equation. So then we have plus the slope or the effect of x. So what we want to find is the effect of toppings on the price of the pizza. This number that goes in for b sub 1x is also coming from the same column, but this one is going to come from the row that's labeled toppings. So we plug in our 0 point, and I'm going to round 0.99. And you also don't want to forget to include the x. Just like we have y equals, the x doesn't go away. The x stays in the equation. So this is our regression equation that we can then use to predict or set the prices of pizza for this area based on the number of toppings on the pizza. Now let's connect this a little further. because you'll notice that I also ask you to take a moment to interpret the meaning of these numbers. So when you see interpret, what I'm saying is explain to me in words what this means. I don't want a definition of what it is. I want to know, what does it tell me, or what does it represent conceptually? Now, it'll probably help by first starting by putting in or labeling our y and our x with our variables that they are from our model. For example, the price of pizza based on this model for this data is equal to 9.51 plus 0.99 for each x or each topping that gets added. Okay, so now that maybe helps a little, but what I really want to know is, what is the interpretation of those two numbers, the 9.51 and the 0.99? So let's think about this for a moment. The price of the pizza is equal to 9.51 plus 0.99 for each topping. So what if my pizza had no toppings on it? What would you expect to pay if you plug in a 0 for the number of toppings? What would we predict for the price of that pizza based on our model? Well, if we plug in 0, then this whole term would be 0, because anything times 0 makes that whole thing 0. So in this case, what would we predict for the price of our pizza? 9.51. So this 9.51, $9.51, this is what we would predict or expect a pizza with 0 toppings on it to cost. All right, so we would predict that a pizza with 0 toppings would cost about $9.51. So this constant is telling us, okay, if there were none of x, then what would we expect for y? That's what the constant represents or means. So if you see this on a test, which you are likely to do, I would want you to interpret the meaning of those numbers. I want you to give me a written explanation like this. Put it into the context of the problem. If we're talking pizza, tell me it's what we predict the pizza would cost if there's 0 toppings on it. If we're talking something else, like height and finger length, then you could tell me this is what we would expect somebody's finger length to be if they have 0 height. It doesn't make a whole bunch of sense, but it is literally what that constant is telling us. If we had 0 of x, what would y be? So that takes care of the first number. But what about the second number, the 0.99? So yes, that is the slope, but that's not all that I'm looking for here. I want to know, what is this 0.99 telling me about the relationship between my x and my y? So here, this is saying that, okay, if I had a pizza with 0 toppings, I would expect it to cost $9.51. What if I put 1 topping on it? Then this 0.99 times 1 would equal 0.99. So how does the price of my pizza change by adding 1 topping or by increasing my x by 1? That's saying that we would increase the price of the pizza by that 0.99 by the b sub 1, by our slope. So this is telling me that for each topping added, add 99 cents to the price. In other words, as x, or toppings, goes up by 1, y, the price, changes by how much? It goes up, because we have a plus here, plus 0.99, it goes up by 0.99. So as toppings, or x, goes up by 1, the price of the pizza changes by 0.99. It goes up by 0.99. Okay, now finally, let's interpret the correlation. Often you hear regression and correlation talked about together because they go together in this type of model. The regression is the center, and the correlation represents the spread, or how spread out our data are. Now we find this information by looking at the model summary table. That's the first table in our JASP output. You can see this is where these values came from. So we're going to talk more about correlation, but for now we're going to focus on just a basic explanation of R squared. R is the correlation, but we want to focus on R squared from this output. Now, if this R squared value was a 0, then this would mean that the toppings model that we just built doesn't explain any of the variability that we see in pizza prices around the mean. A 0 means it's explaining 0% of the variability. On the other hand, if it said 1.00, then that would mean that our model is explaining 100% of the variability in pizza prices that we see. So I want you to think of that R squared value as going from 0% to 100%. So a low number close to 0 means our model isn't explaining very much of the variability in pizza prices. It's not very good. It's not very helpful. A high number close to 1 means our model is explaining a lot of the variability in pizza prices. So it's a really good model. It's helping us to explain a lot of the variation. So how would we interpret this R squared here? If our R squared is equal to 0.353, this means that our toppings model, and I'm going to convert into percentages here by going 2 decimal places to the right. So this R squared of 0.353 means that our toppings model explained about 35% of the variability in pizza prices. So about a third, or a little over a third, of why we see the price differences, the differences in the variability in pizza prices, about a third of that we see is due to toppings, according to our model. Now keep in mind that there are a lot of other things that influence pizza prices, besides just the toppings. The quality of the ingredients, what style place it is. Are we talking like a Little Caesars or California Pizza Kitchen, or maybe somewhere that's like ultra gourmet? So there are a lot of different factors besides toppings that affect how pizza shops price their pizzas. According to our model, the number of toppings explains about 35% of those differences we see in prices. This means that other stuff, other information, is explaining the rest of the variation. In other words, we've explained 35% using toppings, which means that 65% of the variability that we see here in prices is unexplained by our model. So pizza price differences are not explained with just toppings. We would have to maybe look at other variables and add them to the model to explain more of that variability that we see. Okay, so that wraps up our introduction to running a regression, writing a regression equation and interpreting what it means, and interpreting how good our model is in terms of explaining the variation that we see. Now, I've also added some completely optional extra practice for your upcoming test, which is the last 2 pages of this classwork, or 3 pages. I would recommend that if you want to get some extra practice, you work through these pages. All the information that you need should be provided for you without having to get into JASP. Now, if you do want to run the JASP yourself to practice that skill, then these data files are also available in this week's module. So they're split up so that you can run them separately. There's one for pizza prices for hipsters and one for pizza prices for working class. Now, this extra practice is basically going back through again, making simple models for the hipster areas of LA and one for the working class areas of LA using the information provided, and then working through and building an additional model by using toppings again, right? And looking at each of these different sections. I can tell you that the structure of this practice is very similar to the structure of the first exam. So if you spend some time really trying to understand this, it will help you a lot on that midterm test. It will make it much easier. I will fill out my answers and post them in a few days so that you can check your answers against mine. And other than that, I guess let me know of any problems that you have, and I will talk to you soon.